Hello, I'm Dongdong Chen from the University of Edinburgh. Today I'm very happy to present our ICCV paper Equivariant Imaging Learning Beyond the Range Space. This is a joint work with Julián, Tachella, and Davies. Imaging systems capture noise measurements y of a signal x through a linear operator a, that is y equal to x plus epsilon. This is also called as a forward model of the imaging system. The target of the inverse problems is about to recover the signal set x from only measurements y. One of the biggest challenges of inverse problems is that generally the solution is not unique since the operator a is U-post. In practice, according to the different forward operators a, there are many applications of inverse problems. For example, compressed sensing MR, sparse-view computed tomography or CT, image super resolution, and inpainting. Typically, the inverse problem can be solved by a model-based optimization, which boils down to a maximum or posterior problem. Generally, the model-based solutions can provide physics-plausible image reconstruction. However, these methods typically require strong prior knowledge of X, such as sparsity, and they also suffer from the long running time. Recently, deep learning or learning-based techniques has become a new paradigm for solving the inverse problem. The deep learning methods basically use the training samples to learn the reconstruction function f y equal to x, and then apply the trained neural network to predict the reconstruction for the testing samples. Basically, the learning-based solutions can be divided into two categories: the supervised, which need paired or unpaired x and y to train the net; the unsupervised, which need multiple operators ak to capture the loss-based information. However, we're wondering, what if neither ground truth nor multiple operators are available for learning? In this work, we aim to learn the reconstruction function fy equal to x, where, first, there are no ground truth data xi for training. This setting is important in practice because most inverse problems don't have ground truth. Secondly, only a single forward operator A is available. Finally, A has a non-trivial loss base. This is a very challenging setting because we have low information about X outside the range space of A pseudo inverse. For example, in geometry, the oracle singular X can be decomposed as the sum of two components from the range of A pseudo inverse and the loss space of A. Obviously, under our challenging settings, we can only have the range component A dagger y. So, it is fundamentally impossible to learn the singular set X using the measurements data yi alone. In order to learn beyond the range space of A pseudo inverse, we can exploit some mild geometric priors about the set of plausible signals X. We argue the natural signals enjoy simple but fundamental geometric priors. First, we assume the signal set has a no-dimensional structure. Second, we assume that the signal set X presents some symmetries, that it is invariant to certain groups of transformations such as shifts, rotations, reflections, etc. This assumption has been widely adopted both in multiple signal processing and computer vision applications. For example, it is commonly assumed that nature images are shift invariant. Another example is computed tomography data, where the same organ can be imaged at different angles and making the problem invariant to rotation. Based on the mild low dimensionality and invariance assumption, we have the following key observations. First, invariance provides access to implicit operators AG equal to ATG with a potentially different range spaces, where the orthogonal matrix TG is a transformation matrix. Second, for any X in the singular set and any transformation in the group, the composition F and A is equivariant to the transformation Tg. This is very important because it tells us which properties the reconstruction function should have. It also derives our equivariant imaging algorithm. Now, we know that for any x in the signal set and any transformation in the group, the reconstruction function f should enjoy. First, the measurement consistency AFY equal to y. However, as we introduced before, this constraint is not enough to learn a good f because it can't capture information about x outside the range space of a Poisson inverse. Second, based on the invariance assumption, the f should enjoy the invariant set consistency. FATGAX equal to TGFAX. The right is an example of learning with and without equivariance in a trial 1D signal inpainting task. The signal set consists of a different scaling of a triangular signal. On the left, the dataset does not enjoy any invariance, and hence it is not possible to learn the data distribution in the law space of A. In this case, the network can inpaint the signal in an arbitrary way, see the green parts, while it achieving zero measurement consistency loss. On the right, the dataset is a shifting invariant. The range of A is shifted by the transformation Tg, and the network inpaints the signal correctly. Finally, in most cases, not only is the signal set X invariant, but also the distribution Px defined on the set is invariant. So we can also enforce this distribution constraint when learning the inverse mapping F. Accordingly, we propose a training strategy that enforces both the measurement consistency and the equivariance using only a dataset of a measurement data y. We define the reconstruction f theta as a composition of a unit and a Poisson inverse. In the forward path, we first compute x1 equal to f theta y as the estimate of the actual ground truth x, which is not available for learning. Note the measurement consistency between AF theta y and y only ensures that AX1 stays close to the input measurement y, but fails to learn beyond the range space of a Poisson inverse. According to the equivariance property, we subsequently transform x2 equal to tgx1 for some g in the group, and pass it through F composite A to obtain x3. The network weights are updated by minimizing the following training laws, where the first term is for measurement consistency and the second term is to impose equivariance. Alpha is the trade-off parameter to control the strength of equivariance, and L is an error function. In practice, the ER algorithm can be done with only 4 lines of code. As can be seen, the equivariant imaging is self-supervised, end-to-end, and physics-based. We can add an additional plurality to enforce the invariant distribution consistency. Inspired by generative adversarial networks, we use a discriminant network D and adopt an adversarial training strategy to further enforce that x1 and x2 are identically distributed. The resulting adversarial equivariance learning strategy is aimed to solve the following optimization, where beta controls the strength of an invariant distribution consistency. A necessary condition for recovering the single model X from the observations Y is that the below stacked big matrix is of rank M. This necessary condition provides a lower bound on how big the group G has to be. It at least satisfies M times the size of group should not less than M. Accordingly, another necessary condition is that the range space of a Poisson inverse is not invariant to the action of the group G. So, in practice, we should pick the reasonable transformation to a specific inverse problem according to the physics of its forward model. For more detailed theoretical guarantees, please check our latest paper. we evaluated the performance of EI for the sparse-view CT image reconstruction task. We trained different models on the real CT image dataset CT100. We used the 50 views random transformations as the forward model and the iRandom as its preceding inverse operator. We applied the random rotations of the transformations group. As can be seen, firstly, the EI algorithm works as well as the fully supervised trained model. Secondly, the EI reconstruction is 7 dB beta than the preceding inverse reconstruction. This is clearly demonstrating the correct learning of the loss-based component of the image. We also evaluated the performance EI for the natural image inpainting task. We trained the models on the natural image dataset of 100. In each measurement image, a fixed set of 30% pixels are dropped. In this example, we applied the random shifts of the transformations group, as the natural images are generally shift invariant. We can see that in this example, there is about only 1 dB gap between EI and the supervised reconstructions. And the EI reconstruction is a 20 dB beta than the preceding inverse reconstruction and the measurement consistent reconstruction. In this paper, we introduced a lower self-supervised learning strategy that can learn to solve an yield post-inverse problem from only the observed measurements. EI exploits simple but fundamental priors about natural signals, symmetry, and low dimensionality. The code has been released. Please scan here and have a try. Thanks for your attention. If you have any questions, please come to my poster and talk to me.